we get this. Okay? And if now I just develop this a little bit, I put a p here, so that this is p plus 1 minus 8p of it. Well, and what we got in the denominator is a quantity p plus 1 minus 8p, which already appeared before. This is, by definition, the number of rational points on the elliptic curve modulo p. So this is by definition of AP. AP was defined so that this is equal to this. Okay? So, you will agree with me that although, okay, so this is already the, okay. So now you will agree with me that if this had some sense, which doesn't have because this is not convergence, so therefore this is infinity. But if this had some sense, the more points the elliptic curve has, if this curve has high rank, it means that over Q it has many points. When we reduce mod P for all times P, this will again have a lot of rational points in the reduction mod P. And this will mean that these quantities in the denominator are much higher than P. Okay? And this is much higher than P. This means that this denominator wins, so to say, and therefore tends to 0, if this has a meaning. And if the rank is very large, this will tend to 0 very quickly. Okay? So you could expect that if the rank is very large, this would be 0 to a high order. This has no meaning, and the correct interpretation is this one. This is the correct statement. And this is just nonsense, but perhaps intuitively useful for you. Okay? This is at least what Birch and Swinnerton-Dyer explain themselves, that this is the idea that they have in mind. It's not out of my mind. Okay? So let me write it. If R is big, we expect these quantities to be much bigger than P for large P. And hence, this meaningless expression, we should expect it to vanish to high order. Okay. Okay. So, what do we know about this conjecture? So, of course, it's impossible to prove if we don't prove first that this function extends to the whole complex plane, because otherwise, not even the statement makes sense. But since this modularity conjecture is proved for integral Q, it makes sense to try to prove it. And there is the following theorem of Gross, Zagier, and Kolivagin. It's a theorem from 1987, which is the following. Assume the ground field is Q. So that we already know that the conjecture makes sense because we can indeed evaluate this function at s equal to 1. And assume that the order of vanishing at s equal to 1 is 0 or 1. Okay. Let me call it, if I have to refer to this very often, I call it the analytic rank. Okay, this will be in order for me not to write every time the order of vanishing of the function. I will often refer to this order of vanishing, the analytic rank. In this terminology, the conjecture of Birch and Swinnerton-Dyer predicts that the rank is equal to the analytic rank. Okay? So, under this hypothesis, Rotger and Elliptic proved that the conjecture is true. Okay, let me just call it BSD. Okay, so perhaps you will say, well, so this means that these guys, they have proved the conjecture for almost all elliptic curves, because if we expect that 100% of the elliptic curves have rank 0 or 1, these guys proved BSD for 100% of elliptic curves. Okay, and this is true. We do expect that BSD is already proved for 100% of elliptic curves. Okay, so of course we still don't know that 100% of elliptic curves have rank 0 or 1. And even if anybody, Varga, proved that indeed 100% of elliptic curves have rank 0 or 1, this would still mean that there are infinitely many elliptic curves of rank 2 or more, for which we don't know. Okay? Also, notice that this is a theorem for elliptic curves over Q. For elliptic curves over general number fields, this is not a theorem. It is open. When the number field is a totally real field, as before, this theorem has been extended to a large extent by Zhou-Zhang. Zhou-Zhang, this theorem has been generalized to a large extent to totally real number fields by Zhou-Zhang. Okay? So well, in a sense, you can think that the conjecture of Birch and Swinnerton-Dyer is known to a good deal of it. Okay? Or if you are more pessimistic, you can think that no, we are very far from proving it, because there are infinitely many curves of rank at least 2, for which we have no idea. Okay? So at present, most of the efforts are devoted to try to prove it for curves of rank at least 2, or for curves over larger number fields. Okay, these are the two directions of research. Okay, then there are also generalizations of the conjecture to other objects like abelian varieties or motifs, depending on your background. If you know what an abelian variety is or what a motif is, there are also conjectures which generalize the conjecture of Birch and Swinnerton-Dyer to these more general settings, and these are conjectures by Davidson and Bloch. Okay, so now I have two goals in mind in the time I have left. So depending on time, I will spend more details or less. But I would like to give some of the ideas behind the proof of the theorem of Mordell-Weil, this theorem that the very first fundamental theorem that tells you that the group of rational points over a number field of an elliptic curve is finally generated, so it has finite rank. Because some of the ingredients, especially an object called the Selmer group of an elliptic curve, appears, and it's an interesting object that we will study later. And the other thing that I would like to explain a little bit is some of the ingredients in the proof of the modularity theorem, the theorem that tells you that the L function extends to the whole complex plane and satisfies a functional equation, because some of the ingredients involved are modular curves and modular forms. So these two objects, Selman groups on one side and modular forms and modular curves, will be very important for the remaining lectures. So, okay, let me.
I have a question before you go on.
Yes.
Do we know of the existence of a single elliptic curve with an elliptic rank higher than 4? Higher or equal than 4?
I would say no. I would say no. We know of curves having
And
rank
rank
3 or 4. Yeah, analytic rank 3 because of the working percentage here. But 4 or more, no. So that's a good question for you to understand what is our knowledge. We are not even able to produce elliptic curves such that the order of vanishing is 4 or more. We are sure that they are there because we know of examples of elliptic curves having rank 4 or more, but being able to prove that the analytic rank is 4 or more is a difficult question. Yeah.
Is there some algorithm which determines the analytic rank of the curve?
Is there any?
An algorithm.
Well, you can, sure, because what I did not in a way that you can prove it, but that you can have a numerical approximation, yes, because you can numerically approximate these values. Of course, proving that something which looks like 0, proving that this is 0, it's very difficult. You can show in the computer it's 0,100 zeros, but you still cannot prove that it is 0. But you can believe the computer. Oh, yes, there are algorithms. If you like these kind of questions, there is this book by William Stein, which is called A Computational Approach to the Conjecture of Birch and Swinnerton-Dyer, where these kind of algorithms are explained. Okay, so ideas behind the modularity theorem. So it says that for an elliptic curve over a numbered field, or just for simplicity now over Q, this is isomorphic to Z to the R plus a finite group, the torsion function, which is finite. Okay, we want to prove this. Okay, this is the theorem, and we want to prove this. And Fermat, the ideas of descent of Pierre Fermat already show that this is equivalent to proving the following. You start with this group that you just know that this is an abstract abelian group, and if you prove the following two statements. First, that for some positive integer, this group is finite. The quotient is finite. Of course, if this is true, this is automatically true. But in general, you have an abstract group, and you can show that this is finite. This does not imply that this group has this shape. But if you add a second condition, then this is equivalent. And this is a condition that we won't study in more detail, but I just put it here. There is a sort of function which people call a height function. this is a sort of function that you were asking before. When you have a point of the curve, this will have some coordinates, x and y, and the height function is simply measuring how big the size of these coefficients. Okay, so it's like a sort of improved absolute value of the maximum of the absolute values of x and y. Okay, so there is a height function satisfying some suitable properties. Okay, and I'm not going to spend time explaining exactly what kind of properties, and I'm not also going to spend time explaining why these two statements are equivalent, because they are not so relevant to what I'm going to use for subsequent lectures. We can read, but can you read it well? Okay, so but I would like to explain a little bit why this is true. Okay, why there exists some positive integer such that this quotient is finite, okay? Which is an obvious consequence of what we want to prove. And together with this black box, perhaps, in these lectures, this implies the model rate theorem, okay? So, some ideas for proving that this quotient, and here I will take n to be a prime number p, is finite. Of course, if this is true, then this quotient is finite not for some n, but for all n. Okay? But these ideas of Fermat show that if you prove it for one n, and there is this kind of height function, this already implies the statement that you wanted to prove. Okay, so this prime p will be any choice of prime, not dividing the exponent. Okay. Okay, and now, so define. So the idea is embed this quotient inside some other group that you can prove that is finite. Okay, and the group we will call the Selmer group of Elliptic. Okay, so this group is very important for many purposes, and in fact, it's a very useful technique to replace the Mordovai group of elliptic curve by its Selmer group, because one believes that the difference between these two groups should be controlled, at least conjecturally, and therefore statements that you could make about this Selmer group should have some consequences about the Mordovai group of elliptic curves, which is the object that you are mostly interested in. But it happens very often that you can prove theorems for the Selmer group of the elliptic curve as a substitute of the Mordovai group of the elliptic curve. Okay? So let me introduce what is this Selmer group. In order to define this, define the following. Let E of square brackets P be subgroup of P torsion that I already introduced before. This is isomorphic to Z mod PZ as an abstract group, and moreover, this finite sum group has a natural action of the Galois group on it, because this elliptic curve is defined over Q, But the points themselves are not rational over Q in general. They are rational over Q bar. And therefore, the Galois group GQ, the absolute Galois group of Q bar over Q, acts in a natural way on the coordinates on EP. Okay? Giving rise to what people call a Galois representation. So every Galois element acts on the p torsion elements in a linear way, and therefore it induces a homomorphism into a group which is isomorphic to GL2 of ZP. GL2 because this is isomorphic to two copies of ZP. Okay? This is what people call a Galois representation. And I will use the following notation. If you know Galois cohomology, this is the standard notation. And if you don't know Galois cohomology, don't worry at all, because I'm going to explain you what I mean by this. This will be the what people also call the group of extensions of Z mod P by EP. And by this, I mean the following. I mean the set of isomorphism classes of exact sequences where here there is EP, here there is some M, and here there is ZP. Okay, so this should make sense because this is not a very complicated object. We are looking for all possible M's such that you can find an embedding of this P torsion into M and the projection of M into ZP in such a way that the kernel of this map is equal to the image of this map. And these are maps, homomorphisms of abelian groups respecting the Galois action. So M should be an abelian group equipped with an action of the absolute Galois group. And here you already have a Galois action, and here I put the trivial Galois action in which the Galois group acts in a trivial way. Okay? And then you say that two objects like this are equal or isomorphic if we can put the two exact sequences in a way that there is a commutative diagram where everything is isomorphic. Okay? So, this is what I call this H1. And the Selmer group is a subgroup of this H1. The Selmer group of P over Q is a subgroup of this H1 is a subgroup of those extensions, those M, on which GQ acts in a good way when restricted at all prices. So I'm not going to give all the details. I'm going to explain them a little bit in words if you have the background, but otherwise don't worry. You consider all possible m's fitting inside such an exact sequence together with an action of GQ. And now, inside GQ, for every prime P, there is a subgroup which is called the decomposition group at P.
Primes L.
Yes, sorry, because P here is a fixed prime P, and now I'm talking about all possible primes, not only P, but all primes L. Okay? And what I'm saying is that when we restrict the action to the decomposition group at L, this action should be good in a subtotal way. For primes L, which are different from P and not dividing the discriminant, we are just saying that the inertia is acting trivially, and that primes dividing the discriminant will just have to define it in a more symmetric way. Okay, but it's just a subset. And the map is the following. The map that I was talking about. Should I go here? The map I was talking about is the following. Take a point X, call it delta. Take a point X in your Q. I have to define an extension M attached to X. And this will be the image of this map. So I have to define for you what is this MX. We call it MX must be an abelian group such that there are maps such that we have this diagram, and MX at the same time it has to be a Galois representation. There must be an action, a linear action of the Galois group of Q acting on it, where MX is defined as follows. Okay, so let me explain it. In order to explain how can we construct this extension MX fitting in this diagram, perhaps I can start with an observation that all you know about singular cohomology, which is the following. If you consider the elliptic curve over the complex numbers, and you delete the point of the origin, and delete also, remove the point X, and you consider the singular homology, these are just paths. Here you have removed 2 points, and these are just paths on this Riemann surface where you have removed these 2 points. There is a natural map from these two, the H1 of the elliptic curves without removing any point. Okay, so this is just the elliptic curve where you didn't remove any point, and therefore this path, for instance, which is not trivial here, goes to 0 here. Okay, so this is isomorphic to 2 copies of Z, and this is isomorphic to 3 copies of Z. This is surjective, and the kernel is 1 copy of Z generated by one of the facts around the point. Okay, so this exact sequence of homology singular homology groups has an analog in all possible homology or cohomology theories that you can think of attached to an algebraic curve or to an algebraic rank. So this exact sequence in singular homology has an analog in what people call étale cohomology. So depending on your background, you will know what étale cohomology is or not. But you now probably can believe me, even if you don't know what étale cohomology is, that in étale cohomology, there is an analogous exact sequence diagram, which, since it's cohomology and not homology, it's reversed. So we have here the group that we had on the right. Here we have it on the left, but this is now étale cohomology. This is the elliptic curve over Q bar. Here I can put any coefficients. This was true for Z, but also for ZP. So I will put here ZP. Here in the middle, I have the same object, minus 2 points. And on the right, we have what we had in the left. But since I'm using ZP coefficients, instead of writing Z, I write Z plus P. Okay. And if you look at the definition of étale cohomology, it's not a complicated definition. This is, by definition, the group of étale coverings. This is why it's called étale cohomology. The group of étale or unramified coverings of degree P of this elliptic curve as an algebraic.
So you're actually taking this Wald-Davidson approach to
Exactly. There are many approaches for defining this map.
sequences.
I am explaining this approach because this is the one that generalizes the best for the approach I will take later in subsequent lectures. Okay, so one can prove that this is isomorphic to EP, and in fact, this is an exercise that you can do. There is a natural isomorphism between the elliptic coverings of an elliptic curve as an algebraic curve and the P torsion, which is quite easy. And therefore, this also has a Galois action because the Galois acts in a natural way on coverings. And therefore, we got something which depends on X, and this is my definition of the extension I was looking for. Okay? So it's quite basic. I mean, even if you don't have the background of étale cohomology, this is a quite basic definition. And this is a definition for any point. You can also check that if you have a point which is P multiple of another point, the extension that you get is a trivial one, the Cartesian product of the left and the right, and therefore it factors to this quotient. And then all that you need to do is proving that this is finite. And this is finite thanks to a classical theorem due to Hermite and Minkowski. Okay? So this was some of the rough ideas in the proof of the model page. Any question? If there is anything, okay? I mean, if you know these things very well, here there is a 1, and here there is a 1. So you don't want to write because exactly. Okay.
How we use the assumption that L doesn't divide the discriminant?
That P doesn't divide the discriminant, yeah?
Yes.
That's a good question. Well, perhaps it's not so needed. I should check. But no, but this is always needed. I should think more. Perhaps there are, but I think this sequence is always available. Okay, and now I don't know what time is it. I think it's almost 7. Should I stop here? Or would you like
We owe you 10 minutes from the break.
Are you very tired?
Or if you feel like we can ask you.
No, I would like to spend 10 minutes explaining what a modular form is. If you are too tired, sorry for that. Okay, so let me now explain some ideas behind the proof. Okay, remember that these were the two key properties, that all elliptic curves over Q satisfy, and that in fact we expect to satisfy even if it's an elliptic curve over an arbitrary number. Okay, here you will see why we can prove it when the elliptic curve is defined over Q and not for an arbitrary number. Okay, so the base field is very important. We expect the same to happen, but the proof is the fact that the ground field plays an important role. Okay, so I take it out as an excuse in order to introduce for you what are modular forms and which are the relationship between modular forms and elliptic curves. Okay, so let n, this will be a positive integer, be the what people call the conductor of the elliptic curve. This is a positive integer which satisfies that the prime numbers that divide n are those at which E has good reduction. Okay? I'm not going to define it, but okay, the prime divisors n are those at which E has good reduction. And good reduction means bad reduction. Yes, thank you. And having good or bad reduction means that we can find some Weierstrass equation of the elliptic curve at which this prime P divides or does not divide the discriminant. Okay? If a prime P does not divide the discriminant of the Weierstrass equation, this means that it has good reduction. But if the prime P divides the discriminant, it could still happen that you could find some other Weierstrass equation for which the discriminant is different, that the two curves are isomorphic, and which P doesn't divide the discriminant. Then we still say that if P doesn't divide the discriminant, the curve has good reduction. And those primes P that divide all possible discriminants for all possible Weierstrass equations with the curves are those that we call of bad reduction. Okay? And the conductor of E is defined in a different way, but it has this key property. It's divided exactly by those types of bad reduction. And the exact power at which P divides the conductor depends on the geometry of the elliptic curve modulo P, and how bad are the singularities. Okay? So this is a very important invariant, a more conceptual one. It's not so easy to define. It's not just given by a formula with the discriminant, but it's an important one. And using this n, define a group that people call gamma 0, gamma naught of n. This is a group of 2 by 2 matrices with integral coefficients and determinant 1. Defined by those matrices A, B, C, D, which are integers, as I said, the determinant is 1, and such that n divides C. Okay? This is a group which this has finite index. This is an inclusion that which has finite index. And this SL2 of Z is including SL2 of R. And I write this here because this big group acts in a natural way on what people call Poincaré's upper half plane. These are the open subset of the complex plane whose imaginary part is positive. These taus already made an appearance at the very beginning of my talk when I said that a complex torus can be written as a complex plane modulo lattice. There is an interesting relationship between these two notions. And the action is as follows. If you have a matrix, A, B, C, D, and you have a tau, you just define it by what people call the Moebius transformation, which is simply A times tau plus B, C tau plus D. So you can prove that if tau has positive imaginary part, this also has positive imaginary part. And therefore, you can define the upper half plane, and you can identify 2 points on the upper half plane if these 2 points are mapped one to each other by some element in this discrete subgroup. Okay, so this is the quotient where you identify 2 points if they are related by a matrix in gamma node. Okay, this has a natural structure of analytic surface, and this is what we define as x naught of n. Or more precisely, when you look at this, this has a, as I defined it, this is just a set, but you can equip this with a natural topology, which makes it into a Riemann surface. This Riemann surface is not compact, but there is a natural way of compactifying it by adding a finite set of points that people call cusps. Okay, this finite set of points is indexed by the rational numbers together with infinity, quotient by a natural action of not of n on this. This is a finite set. This is what people call finite set of cusps. And there is natural topology of this quotient, which makes this union a compact Riemann surface. Okay, so it looks something like this. Okay, good. Okay, and among all possible points, there is one distinguished one, which is the one that corresponds to the cusp corresponding to the infinity here. Okay? So cusp infinity corresponds to the limit. These are the upper half plane. And you go in this direction, so IT, where t tends to infinity. This corresponds to a point at infinity, and this corresponds to this cusp that we added in order to compactify. Okay? And there is a theorem of Shimura which says that this compact Riemann surface is actually the set of complex points, the underlying manifold of an algebraic curve which has a canonical model over Q. There is an algebraic curve which by a use of notation I will denote by the same symbol, x out of n, defined by the Q, whose complex points are identified in a natural way with this Riemann surface. Okay, so this is an abusive notation because I use the same symbol, x not of n, for two different things. This is a Riemann surface, it's a complex manifold, and here I use the same symbol for an algebraic curve over Q, but allow me this identification because when I look this curve over Q and I look at its points over the complex numbers, this is identified with what I defined before as x of n. Okay, good. And the point at infinity belongs to x naught of Q. In this model, when I say that there is this curve, this means that this is given by a polynomial equation in two variables, and the point at this at infinity has coordinates x and y, which are both rational numbers. Okay, and a local uniformizer of this curve at this point is the function Q of tau okay. Notice that since the cusp is identified with a limit of it when t goes to infinity, when you replace it here, this goes to 0, and this map identifies the upper half plane with the disk sending the cusp of infinity to the origin. Okay? Good. So the theorem of Wiles is the following. There is a regular, a holomorphic, one form that I will call omega e on this modular curve, whose power expansion at infinity is given with respect to this uniformizer as follows. It has the following expansion. Where these ANs, for when n is a prime p, are equal to the quantities that I defined before for the elliptic curve. For all prime p, okay? So, in other words, there is some magic thing here because you start with the elliptic curve. For every prime p, for every good prime p, you reduce modulo p and compute the number of fp rational points. This is a final number. From this, you can compute this a sub p of e. And Wiles' theorem tells you that if you put all these APs together in a power extension, they correspond to the Taylor power expansion of a holomorphic one form on this modular curve. Okay? So there is some correspondence between elliptic curves and holomorphic one forms or modular curves. Holomorphic one forms or modular curves are what people call modular forms of weight 2. Okay? This expansion, the one which is inside the parentheses, the formal expansion F, sub P if you wish, is what people call a modular form. And modular forms, by definition, are power expansions of this shape, where ANs are complex numbers, satisfying some transformation rules under the group gamma naught of n that I introduced before. Okay? According to which are exactly these transformation laws, you say what is the level of the modular form and what is the weight. In this case, it's a modular form of weight 2 and level n. And in general, you can define what is a modular form of weight k for any positive integer k and any level n. Okay? And the notation is that this is an element in n2 of n. This is the space of modular forms of weight 2 and level n. Okay? And the fact that you prove is that the L series that you wanted to prove that it can be extended to the whole complex plane and satisfies maximum equation, this has the following expression. So it's 2 pi raised to the power of s divided by the gamma function times this is what people call the Mellin transform of S. This is an expression which is just an exercise. It's not difficult to prove this. The real deep theorem is this one. And from this integral description, representation of the L series, now you can prove very easily these two statements. Because, for instance, the functional equation is simply replacing s by 2 minus s here. And this is just a change of variable, and you can really show that this change of variable relates this expression to the same expression replacing s by 2 minus s. Okay? And this then allows you to extend analytically this function. So among everything I explained, the real deep statement is this one. That these coefficients that you define for elliptic curve by reducing modulo p the elliptic curve, it's a very naive thing. When you put them together, they are the coefficients in the power expansion of something which is a holomorphic differential form on this curve that I do. Okay, and I
what do we know about coefficients with the index, for which the index is not a prime number?
Okay.
Expressed.
Oh, the index is the coefficients AP with p prime number determine in a unique way all the remaining coefficients.
Okay.
Okay. So for instance, APL, or P and R primes, is simply AP times AL. Okay. So giving the APs already determines the ALs. Okay.
And another question is that x0 of n does actually depend on the integer n, not on the elliptic curve. Right?
That's a very good question. If you have two different elliptic curves with the same n, which happens, these two elliptic curves give rise each to a different modular form on the same modular.
Yes,
That's a very good question. So that's it.
Let us thank Victor for a very nice and clear lecture. One question, please. One question, please. not leave this room without asking questions.
You can also ask me more informally.
Yeah, I have something I've never understood in this business about Mayan's cost. Do we believe that the modular form is always the pullback of the neuron differential itself?
Yes, and it's even proved, if not for all cases, but in many cases.
More questions? Let's thank the speaker.
And that's why you only need to add I that you interpret all this it's actually the same. I
So these people should stay Are there any more questions?
Хочешь заняться впечатленно, согласись, я вот был сегодня на этой фигне, Нет, я не сказал, что не надо идти на это. Ну, ты как-то говорил, я учительный, я тебе поверил. Говно вполне. В смысле? На первые полчаса было это был самый говно. Вообще он, короче, просто доказывал какие-то вещи, которые не определил. И там очень долго распинался, и рассказал какую-то группу, которую он не определил действий, там на чем-то, что он не определил, и говорил, что и там был какой-то исторический справка о том, что это доказал. Вот это вот утверждение, ничего непонятно, доказал тот чувак. А на самом деле его доказал не тот чувак, а называется того чувака. Я пытался. А потом нет, ну понимаешь, да, слушай, ну как понимаешь, что с самого начала ты 40 минут, а 20 час. На не самое начало пришлось 20 минут, и он тоже ничего не сделал. В общем, нет, кстати, там искали этих докладчиков на тех, кто там спросили про опционный вопрос, политическую теорию. Вот, и искали докладчика, он в следующий раз будет рассказывать с мной Адамса. А кто были? Это там старый чувак, который сидел на первой партии слева. А, на первой партии это слева? Ну, как он там Антон, нет, это доказывал эмоционально. Это старый чувак, старый. Ну не старый, ладно. Старый, в смысле, лет там больше, чем Антон. Ой, я не знаю. Это представляешь. А что все, кто младше, Антон физические дети, все вкуснее. Да, это знаешь, только Антон. Причем он еще смещается все время. Нет ничего абсолютного. Да, но при этом все время в самом соку. Именно так. Слушай, пойдем, правда. Пойдем к ним. О, что ты такое? Заметь, что я вернусь.
Был вопрос про то, что неизвестно этих штук, у которых
хотя бы читаю.
Я не знал с этим вопросом, но мне казалось, что смысл функции мы можем что-то подписать.
Нет, но с другой стороны, я тоже так смотрю. Вот как для конкретной прямой, для конкретной прямой вычислишь все АП. Вот как? Ладно, для поля это можно сделать.
Нет, понимаешь, мне придется начать с двойки и тройки, а
ну нет, что мутно, наоборот. Тебе же достаточно только уравнение, что у тебя уже есть.
Подожди, вот ты действительно непонятно, в чем проблема.
Нет, для всех. Для всех и сразу, потому что у тебя такое произведение. Нет, ты не веришь, что нет способа. А вот неприятно совсем. Это не нравится мне. Это не текст называется.